Now we're going to talk about what is beneath our feet, Earth as a planet. So other than its shape, what do we know about the Earth? Well, it has a mean radius of about 6,371 kilometers. Now that, of course, depends where you are, because we said that the Earth was an oblate spheroid, which means actually at the equator, the radius would be larger than we would find it at the pole. From the center of the Earth to the top of Mount Everest would be slightly larger than from the center of the Earth to the bottom of the ocean. So you can see this is just a mean distance that we have here. The mass 5.97 times 10 to the 24 kilograms. So that's 24 zeros following the 5 number there. Average density of 5.51 grams per centimeter cubed, where a density of 1 gram per centimeter cubed is the density of water. So the average density of the Earth is significantly greater than the density of water. This thing would sink like a stone. The average circumference, if we measured, of course, the circumference around the equator would be larger than the circumpolar circumference, but taking the average of all the possible circumferences that we might have on the Earth, we find the circumference to be about 40,000 kilometers. And what it's made out of? Well, it's mostly made out of iron, 35% in fact. That is the thing with the largest elemental abundance. It has 30% oxygen, and remember that oxygen is present all in the water as well, but it's also present in iron oxide and combined with lots of other chemicals. Silicon, which combined with oxygen forms all of the sand and lots of the rock that the Earth is made out of. And of course magnesium, which is very, very abundant in the Earth's surface. The ancient people had an understanding that the stars moved in the sky. Of course, it was because the Earth turned underneath. And attaching mythological, religious significance to those stars, they imagined that those stars were like the souls of people and that they could see them moving in the sky. Some of them spiraled around the North Star, never ever setting, forever in the heavens, but others disappeared beneath the horizon. They set and they rose elsewhere. So an explanation as to where those stars went, they travelled through the underworld. What was in the underworld? Well, this is basically where some of the ideas of heaven and hell come from. It's not a very pleasant place, and the ancient pharaohs went to great lengths to ensure that they didn't have to travel through the underworld, building great big pyramids around their dead bodies with shafts that pointed out towards those circumpolar stars so that their souls could end up in the heavens in a place where they never had to set and go into the underworld. So moving on into the 1200s, and Dante wrote his famous Divine Comedy. And most interesting, of course, was Dante's Inferno, which imagined that travelling down through the earth, you go through all these layers. Now, this was still connected to religious ideas and the idea that hell got worse and worse and worse and was more and more terrible as you went down. But this layered idea that the earth was like a gobstopper with all these different layers, or like an onion, and as you went down, you peeled away the outer layers and you found that the layers changed as you went down. Though it was, of course, based in religious ideas, this actually has some bearing on what the earth is actually like. Isaac Newton, he realized that something was quite off about the earth when he looked at the mass of the earth, which he determined through his universal law of gravitation. He was able to basically measure the mass, and that was by looking at how quickly the moon rotates around the earth. That the more mass the earth had, the faster the moon would have to travel at its distance to stay in orbit. And by knowing exactly how fast the moon orbits the earth and its distance, he was able to very accurately know the mass of the earth. And of course, we could measure the diameter of the earth. Eratosthenes had basically measured the diameter of the earth, from which we can find the volume. And doing this, he found that the average density was about 5.5 grams per centimeter cubed, significantly higher than the density of rocks we find on the surface. The only conclusion he could draw was that the earth got more dense as you went down towards the center, which actually matches Dante's view that the earth changed as you went deeper and deeper down. In 1906, Richard Dixon Oldham, he was looking at the recordings, the seismic waves recorded from some major earthquakes that had occurred around the world, looking at those instances where the same earthquake was detected in multiple places, sometimes right on opposite sides of the world. And what he noticed was that there was a clear time delay that indicated that the vibration had passed through the Earth, but sometimes the time delay on the opposite side of the world was not quite as expected, as if the actual path of the seismic wave had been disturbed on its way through the center of the Earth. So he hypothesized that in the center of the Earth there must be a core where the actual state of the Earth changed from solid to liquid, and he proposed that the Earth had a core based on the seismic vibrations that he had detected. Then in 1936, Inga Lerman was looking at the seismic records and found a very subtle trace of something very interesting, that some of the waves were going into the core and were actually refracting the wrong way, almost as if they were reflecting off a boundary of something that existed within it. And she hypothesized that in the center of the liquid core there was actually a solid inner core that pressure had fused together. And now this is incredible to think, that the Earth is solid and then it goes down and then it becomes liquid and then it becomes solid again. And so here we have it. As we go down, we find that the crust is the bit at the very top, between 1 and 100 kilometers thick. Beneath that, we have the mantle. This is all solid, but beneath this, it turns liquid in the outer core and solid again in the inner core. So let's look at those one by one. The first and really good question is, why is it so hot as we go down towards the bottom? First of all, what we do know is that all of the planets in the solar system were hot when they first formed. Lots of friction of the materials crunching together, but also the loss of the gravitational potential turned into kinetic energy as all the objects, all of the asteroids and lumps of rock joined and fused together. It all turned into thermal energy, and that thermal energy is still with us after 4.5 billion years, almost trapped by the insulating qualities of the rock above. But other things in the very center, such as heavy elements sinking down and in the process losing gravitational potential energy as lighter elements sink up, and do not gain as much gravitational potential energy as the lighter elements lost as they sank back down. And of course, radioactive decay. The Earth is full of things like uranium, which is slowly undergoing a nuclear process, rearranging those protons and neutrons, forming more stable elements like lead. And also, what we're finding is that as the liquid in the outer core is slowly solidifying into the inner core, there is a huge amount of energy being given off that we call the latent heat of fusion. And so this is what is continually keeping the core of the Earth warm. The inner core is somewhat mysterious to us because we've never seen it. In fact, we may never see it. But we do understand certain things about it. We know such things as how big it is. It's about 1,200 kilometers across, smaller than the moon, but it contains hugely dense material. We think iron, with perhaps some nickel based on what we can see in our solar system, what the Earth was made from. So it's solid, and the temperature of the Earth is about 5,400 degrees at its core, which is as hot as some of the places on the surface of the sun, which is, really quite hot. The reason why it can be solid when it is this hot, it's much higher than iron's melting point, is that the pressure has fused it back together again with pressures in the 300 gigapascals. Now, that is about 3 million times the pressure of the atmosphere that we are surrounded with all the time. And we'll talk about this in a second, but it has a role in producing Earth's magnetic field. The inner core rotates ever so slightly faster than the rest of the Earth. It's actually decoupled from the Earth above. It grows slowly over time as the outer core solidifies on it. Now, if we were to want to have a look at what the inner core looked like, we can actually get a clue from space. Out in the solar system, other planets formed an iron core like our own, but then subsequently broke up, filling the solar system with little tiny bits of debris, iron meteors that turn into meteorites. On the surface, when we look at these iron meteorites, we see these fantastic crystal patterns. Now, of course, crystals grow large when something cools down slowly. What we think is that the time period of cooling for crystals this large, we're talking the millions to the billions of years. Earth's core has been cooling for 4.5 billion years. The crystals of iron in it would be as big as your hand, if not bigger. Though we have never seen the outer core, we know what it might look like because we do see liquid rock coming out of the ground. The lava that comes out of a volcano from its magma chamber is superheated rock that has become liquid, just like what we'd find in the outer core. Now, don't believe that a volcano's magma chamber descends all the way down to the center of the Earth. The magma chamber has probably formed due to pressure in the crust and not descending all the way down to the outer core. Now, this is going to be almost exactly the same as what the inner core is made from, but the slightly lower pressure has not been able to fuse this as a solid, and so the high temperature wins and it is a liquid. Now, this liquid is mobile and flowing and able to move, and it actually forms the main reason why we have a magnetic field around the Earth. So Walter L. Sasser in the 1940s, looking at this evidence, he saw that the core, if it was turning around, would cause vortexes in the outer core, that it would cause net rotation in the same direction in the fluid around it. And that rotation of charged particles is all we need to get to produce a magnetic field that can be detected on the surface. And it's because the core is continually turning inside relative to the outer part of the Earth, that there's this churning in the outer core, and it is that churning that produces our magnetic field. Now, the mantle is quite a long way down. It's between 30 and 100 kilometers down, and we've very rarely, if not at all, ever actually excavated a hole that deep in the Earth. The largest mines that we've dug are significantly smaller than this, but there are a couple of places where natural movements of the Earth has actually pushed some of the mantle rocks up. In Cyprus, they can actually be found on the surface. This picture at the top here is a museum in Cambridge, my photograph of some mantle rocks that have come from all the way down there. And the strange thing about them is that they're nearly all green. They're full of this strange material called olivine, magnesium silicon oxide. And they have very large crystals because they cooled over very long periods of time. But another very strange thing is over very large timescales and to very high pressures, it actually starts to flow, almost like, well, probably the nearest thing is this experiment here. It's called the pitch drop experiment. Now, pitch is a solid substance. We use it to make tar, basically for road building. But what they did over 100 years ago is they put some in a funnel under a jar, and slowly over the space of the century that has occurred, it has flown ever so slowly, like the slowest treacle you've ever seen. Now, what we think about the mantle rocks is over the time period of billions of years, the mantle rocks themselves can kind of distort and undergo flow like this. And it leads to movement in our Earth's mantle, like a convection current, with hotter areas moving towards the surface, moving to the side as they cool down, and then falling back towards the outer core for reheating. And then we think this has been going on, and this is one of the primary mechanisms that heat from within the Earth is actually slowly leaking out into space. But of course, it is such a slow transfer of thermal energy, the inside of the Earth is going to stay warm for a very long period of time. Note that the crust is doing something very strange there. Because of the flowing motion of the mantle underneath, notice there are those little vector arrows on the crust. I wonder what those could be indicating. Well, what a time to be alive, because Douwe van der Meer he works for the oil industry, has been looking at seismic data, and with the breakthrough of supercomputers, has recently been able to map for the very first time the underworld, looking at all of the regions where there are higher and lower densities and higher and lower velocities of moving material within the Earth's core. So this is the very first time that we've been able to literally scan the Earth to see anything other than just the main zones. And then in 2023, Qin Chan and his team came up with the most astonishing findings of perhaps the last decade. And that was when they looked at these maps of the mantle. They found these two ginormous, slow-moving blobs that were very, very close to the outer core, but still they were distinctly different in their makeup and movement to the material around them. And what it is hypothesized these two blobs represent is the impactor, another planet called Theia, which crashed into the Earth 4.5 billion years ago, the explosion from which caused the material to be flung out into space to form the Moon. The fact that we can now scan the Earth and find that a second planet lost for 4.5 billion years can still be resolved on the inside is astonishing. And so here it is. We know this collision happened because, well, we have the Moon. It's a northocite rock, so just like those that we can find in Earth's crust. The Earth's orbital axis, its axis relative to its orbital motion is 23.5 degrees. Something knocked into it to tip it over, and now we've found the remnants of the impactor in the Earth itself. The Earth's crust is the part of the Earth that we are most familiar with because we are stuck to it, and on this surface life has formed. Taken away the oceans here to show you that the actual crust is significantly thicker on those areas of dry land. There's continental crust, and it is much thinner on those places at the bottom of the sea, the oceanic crust. You can also see, identified here, is the edges of tectonic plates. We know that those convection currents in the mantle push and pull and slide the tectonic plates past each other on the timescale of millions of years. And so here we can see it in action. Here is a subduction zone where one bit of the Earth's crust is being pushed under another bit, causing a huge buildup of pressure which melts the rocks, pushing up mountain chains and giving rise to volcanoes, the slow build-up in pressure and then sudden sliding motion, earthquakes. Alfred Wegener in 1912, well, he looked at how the shape of the African continent seemed to match the shape of the South American continent and wondered if at some point they had fitted together. The more he looked, the more he saw that it looked like the jigsaw of the Earth had been broken up and moved apart. Looking at other evidence, he found that some fossils were found in bands that crossed between like South America and Africa as if once they were connected. We subsequently found through the mapping of the oceans areas of the Atlantic Ocean, literally where the plates are moving away from each other, the mid-Atlantic ridge, proving that continental drift has been going on since the very beginning of the Earth. In fact, at the time of the dinosaurs was at a moment when nearly all of the continents were around on one side of the planet, a great continent called Pangaea. It is now broken up and will continue to move for the next 4.5 billion years, or until the Earth is done. Now we, of course, can read the Earth like a book by studying the rocks on the crust. This is the science of geology. We can look at the layers of the rocks and understand when they were placed down, quite often by looking at fossils that we find within those rocks and where they are in the sequence of how recent they must have been put down or how long ago. Some of the oldest rocks we can find on the Earth are about 4,000 million years old, or 4 billion, that had formed immediately after the impact that caused the formation of the Moon. And this has led scientists to dividing up the time between now and the time when the Earth formed into this thing, the geological timescale. And what you can see is that the Earth spent an awful lot of time You can see all that bit in the middle that is a pink colour, basically being a rock. And you can see that we only got a permanent atmosphere of oxygen about halfway through between when the Earth formed and now at 2,200 million years ago, 2.2 billion years ago. And at that point, halfway in the journey between the Earth being born and the Earth's present day, life forms. And that's what you can see is that green band that goes around the outside, and then it gets more complicated, various different things. And then we can see, and the time of the dinosaurs is the little orange band on the left-hand side there. So you can see that the time when the dinosaurs were the dominant species on Earth was that time. And of course, there you can see on the very inside track on where it's blue, there's a little tiny X, an extinction event, the KPG event. That was the death of the non-avian dinosaurs that gave rise to the time of the mammals, and then eventually, in the last 2 million years, the birth of humankind.